everyone. Thank you for having me. Really, really excited to be here. So I'm Ramsey Nasser. This is my website, if you want to check out my work. This is my Twitter, if you're into that. So I do a bunch of different things, and I feel like I get to be a different person at like every different talk I give. So I'm an educator. This is me teaching. Will my Zoom trick work? Yes, my Zoom trick works. This is me teaching the wonders of JavaScript to my students. This does work. I'm also excited there's a whiteboard, so I'm going to get to do my teacher thing later. It's going to come up. I make games. This is actually my primary sort of development activity. This is a hacked Atari joystick that me and a friend turned into a crazy physical game a couple of years ago. But a lot of the software work and research that I do basically ends in the question, like, OK, how do I make a game out of this? Like, whenever there's a new programming language that's proposed, it's like, OK, yeah, how do I make a game out of this? That's not really interesting to me otherwise. I'm also, I have an MFA in design and technology, and I do sort of artworks and like artistic interventions on code. This is an installation for a programming language I designed called God.js, which is a programming language whose syntax sort of parodies high religious scripture and compiles to JavaScript. It's all online. There's like so much stuff I wish I could just like dive into, but it's other stuff to get into. This is the programming language that I probably got the most press of anything I've done. It's called Elb. It's a Lisp whose syntax is entirely in Arabic, which is my native language. And it was made as a sort of act of political protest and sort of provocation because of the reality that all programming is done in American English everywhere in the world without exception. So there's a sort of unintended performance art piece that came out of this that I sort of stuck in now, which is every week, no, not every week, God, every couple of months, I get an email from someone in the Middle East who had like just discovered it for the first time and is really excited to start using it, and they want to know like how they can get into it, and I have to write the same fucking email saying, no, the whole point of this piece is that no matter what you do, this can never exist, because to write software meaningfully, you have to interact with other software and APIs, and those APIs are always in English, and that's a syntax error in this language. So I'm sorry to break your heart, person number 392. So this is the world that I'm coming from. That project was done at an art and technology center in New York called Eyebeam, which supported me for a year doing that research, and I'm very, very grateful for. So I think a lot about the sort of experience of writing code, like what it's actually like in the moment of you pressing those buttons to create something. At Eyebeam, I called the theme of my fellowship was code as a medium of self-expression. This is sort of what I was investigating. And that's what I spend most of my time talking about publicly. What I'm excited about today is I get to talk to you guys about Bytecode, because to make all that stuff happen, I've had to learn about compilers and bytecode and optimization and all the kinds of stuff that goes into building tools that make me and others feel more empowered while writing code, that makes coding less alienating, that sort of achieves all the goals that I want in sort of my relationship with technology. So to do all that like sort of beautiful, high arty stuff, we need to talk about MSIL bytecode. So I titled the talk Symbolic Compilers, A New Hope, because what I want to share with you guys tonight is a new approach to writing compilers that I've sort of come across through conversations with studio mate Kovas, who will come up a little bit later. And it's an approach that I've seen succeed in a number of contexts and applications. One of which I'll demo for you. It's a compiler that I'm building. And it's an approach to writing compilers that is very generic, I think. It can be applied to many, many different things. So I'm very, very excited about it. So the first, I think this is an important question to ask yourself whenever you're setting off on any kind of project, but especially when you're getting into compiler work. Why would you even do this? Everyone knows this, right? It's not a thing. You don't just sort of wake up one day and write a compiler. Compilers take decades to perfect and to get right. The mythology of this stuff is so deep that this is the actual cover of the standard computer science textbook on compiler design. Can we like pause for a moment and like realize that like adults made this decision? It's like, no, compilers, this is dragons, right? Does anyone know what, off the top of their head, what the logo of the LLVM project is? A metal dragon? Like, this is right? I mean, it's a kind of the map where, you know, this is front end, there's a duck, you know, but this is compilers. Don't do compilers. So there's this mythology around like the compilers are just these intractably hard things, and we have to use whatever ones we happen to inherit, right? Because writing a new one is just beyond imagination. And every time someone shows up with a new compiler, it's like, you know, Prometheus coming down from the mountain. So the way I sort of stumbled into it is, again, through that constant search for a better way, a more expressive way to write code. And the test that I always use is making games, because I think making video games is, Brendan Bloom describes video games as being forced to solve every hard problem in computer science 60 times a second. The pressures that you're under are really, really insane. And you know, the success metric is subjective. You can get everything right technically, and just you made a shitty game, sorry. You go out of business now. So through many, many sort of prototypes and experiments, all of which are ongoing, I built a tool with my studio mate, Tim Gardner, called Arcadia. And Arcadia is an integration of the Clojure programming language into the Unity 3D game engine. So it allows you to sort of use an industry-grade game engine, but not program in C#. Program in Clojure, which is this incredible programming language. Actually, I should do this quick survey. How many people here know Clojure or are familiar with Clojure? Oh, OK, that's more than expected. C#? OK, good. That's good spread. Compiler design work? OK, good. I was expecting people to leave the room when I asked that. So yeah, so Arcadia is Clojure in Unity 3D, and it's been a wonderful like journey. It's taken a while to get it stable, but at this point, it's what I use in all of my own like at my company and my personal sort of game projects. It's just all built in Clojure. So this is what Unity looks like. It is actually running right now in the background on my laptop because I'm going to be coding in it in a little bit. But it is, I think the estimates of market share are anywhere between 40 and 50%, definitely on mobile, maybe even beyond that. It is very much the industry standard of like video game development now, for better or for worse. In a lot of ways, it's kind of like what Flash was for interactive web development in the late 90s, right? Again, with all that implies. I'm not. Follow me on Twitter. You'll see what my opinions on Unity. So when I joined the Kitchen Table Coders studio in Brooklyn, and I met David Nolan, who's given a talk here, and Tim Gardner, who's there, they're showing me this weirdo Lisp called Clojure. I'm like, too many parentheses. And I was totally not into it. I was a slow convert. But they told me, they're like, oh, you know, it targets the JVM and JavaScript. I'm like, I don't care about those runtimes. They're dumb. Like, also, there's one weird version of it that targets C#. I'm like, OK, go on. Unity's built on Mono, so I'm listening now. And apparently, there's the main branches of Clojure target JavaScript and Java. But the thing that many Clojure programmers don't know is that there is a version of it that is written in C#, written by this man, effectively, as a hobby project over 5 or 6 years. This man is David Miller. He's the Dean of Computer Science at DePaul University. And there's just this enormous compiler that's just this immaculate, sort of incredible thing. It blows my mind that a single person actually did that, right? Again, going back to the dragons. So with some hacking, we got his compiler to actually run inside of Unity, and Arcadia just totally worked. The problem is, though, that I recently, in the last year, got into console development in my company, and we got dev kits from Sony, and I'm like, hey, I'll use Arcadia to live code my PlayStation. And no, I won't, right? Because while Arcadia runs fine and Clojure and Unity runs fine on desktops, certain export targets like consoles, mobile devices, and Unity's web export, there are restrictions on the kind of code you're allowed to emit. And these restrictions are so tight that the bytecode that we produce, that the Clojure compiler produces, while it's valid C# bytecode, will not actually export to these platforms. And the errors look like this, right? It's some deep mono, I think begin invoke is you're not allowed to use that method in this particular case. So we spent a lot of time trying to hack the compiler to allow it to get it to emit bytecode that would run on a PlayStation or on an iPhone. So this is the real rational answer of why I'm about to share with you what I'm about to share with you. I found myself in a place where I needed more control over the bytecode that my compiler was emitting. To introduce optimizations as well, Unity, the version of Mono that Unity uses has a really embarrassingly bad garbage collector, and there are things that we think we could do about that. Mono has wonderful things that the JVM does not have. It has value types, praise the Lord. It has real generics at the level of the bytecode. All these things are not currently being used by Clojure on the CLR because it's mostly a straight port from Java. So our hope is to sort of be able to bring all of this stuff to the Clojure CLR. So I spent a long time hacking the Clojure compiler, which I need to stress that I'm not at all knocking it for anything. And the reason to not continue on this path is more that this sort of new approach, I think, is just a better style of developing compilers than the more traditional way that this and the Java, the JVM compiler was built. But I spent a lot of time, this is the compiler that I know the best at this point, and I want to walk you through sort of what a slice of that compiler looks like. So people who know Clojure or Lisp, what should this evaluate to? 3, right? So in the sort of, through the eyes of the compiler, this is an invoke expression, right? You're going to invoke the function plus, and the arguments are going to be 1 and 2. So what does invoke expr look like? Invoke expr is a C# class that is a subclass of expr. It's got a bunch of fields. It's got an expression that is the function expression, which you'd expect. It hangs onto its source, I believe, which they don't all do, which is pretty cool. It has a vector of arguments. It uses Clojure data structures to represent parts of the syntax tree, which are pretty cool. So it's got some data, right? It decides sort of what type it thinks it is. So it participates in the sort of typing semantics of Clojure. It does parsing also. Do you see where this is going? It also does evaluation. And it generates bytecode. So this is what the bytecode generation looks like. Where do these come from, right? Where does CLI ILGen come from? Where does obj_expr come from, right? They come from elsewhere in the code. This wouldn't be such a huge problem, but there are 51 of these expr nodes, which are AST nodes in the compiler. So this stuff is spread out and is all over the place. If you want to tweak the typing semantics of Clojure, you have to do it in over 60 files, right? Uniformly. Otherwise, your VM is going to be in a bad place. And Clojure is not a big language. Clojure it's big for a Lisp, but it's tiny compared to most languages, right? So 51 AST nodes is not a daunting number. So because we're hacking on the compiler at the level of just the C# source, we have to rebuild the whole compiler, which takes about a minute to rebuild. So any little idea or tweak you might have, there's just a minute lag between you and between seeing those results. After we build the whole compiler, you have AST nodes that know how to emit themselves. Everything is coupled together and simultaneously spread out, right? hard to iterate on, hard to experiment. Basically, I didn't have a REPL at this point. I started to get the shakes when I don't have my REPL. Long story short, and really what it boils down to is that it's like written in sort of traditional object-oriented style for like a thing of this size. I lean much more towards functional programming, mostly because of successes of projects like this. But you just have stateful objects all over the place, all sort of talking to each other. And dipping in and making small changes to a system like that is very, very difficult. And I say this, because I believe this to be the case abstractly, but also just the experience of trying to do this to this compiler was just dead end after dead end, right? Code wouldn't compile, nonsensical errors. You fix the typing, all of a sudden, the parser breaks. You fix the parser, all of a sudden, we've all been there, right? So a quick sort of overview of compiler theory for people who may be less familiar with it, just to sort of focus the rest of the talk about like what I've been building. So what a compiler does is it takes some kind of source, which a programmer has produced. It converts that into some kind of internal representation, and using that representation, it produces some kind of output in a target. On a target platform. This is the sort of most general way of describing it. For most languages, it looks like this. You have some kind of source code that is represented as text. That text is parsed into what we call an AST, an abstract syntax tree. And that abstract syntax tree is then sort of produces code in the target. So this is generally the text of your code turns into this particular data structure. That's shaped like a tree that describes your code more richly than the text of it did. That can be queried and sort of acted on. So some examples, your JavaScript, when JavaScript gets compiled, it's a JIT compiler, but that distinction doesn't make a whole lot of difference. It gets compiled into some kind of internal V8 AST, and then at runtime, it spits out x86 or ARM, like machine code, right? Something even higher level, like CoffeeScript, has its own sort of CoffeeScript AST that then gets emitted into JavaScript, right? So the state of the Clojure compiler is your Clojure source code is parsed into all those expr nodes, and then those get emitted into MSIL, the Microsoft Intermediate Language, C# bytecode. So the part that I'm focusing on is this last leg, this sort of, given an AST, how are you going to produce your code that's in the target? Again, going back to the original sort of impetus for this is I'm looking for control over my bytecode overall. So this is the sort of part that I'll be focusing on. So the compiler as it stands is this big intractable thing, and every attempt that we've made to sort of hack on it has been very, very slow and hasn't yielded good results. And through conversations with this wonderful man, this is Kovas Boguda, also at Kitchen Table Coders, I started to understand this like alternate form of building compilers. So Kovas built a compiler called Gamma, which is a Clojure DSL for GLSL, which is a shader language. And Kovas wanted to do more interesting stuff with visuals on the web. And he took one look at GLSL, and it's this weird Faco C that's actually a functional programming language that no one will admit. But and it's just he just wouldn't touch it with a 10-foot pole. So he built Gamma. Oh, so I only discovered this after I made my slide, that he had used this slide in his strange loop talk on Gamma, which is just perfect. We're like just totally in sync. This is what Gamma looks like. So it's all just regular Clojure. Everything prefixed with G/ is Gamma code. So here we have your P matrix is uniform, whose name is U perspective matrix, and it's of type. It's a 4x4 matrix. The specifics and the semantics are, they're specific to GLSL. They're not super important. But then he takes this definition of P matrix and reuses it here in the shader, in the vertex shader. which is really nice. So he's multiplying the P matrix by the multiplication of the T matrix and the position attribute. So this looks like normal closure code, right? And that's by design. But what it outputs is a string of GLSL that you could throw at WebGL or throw at your graphics card, and it'll start doing whatever it's programmed to do. So Kovas did two things in Gamma that I think ignited my excitement. The first thing he did was he represented all GLSL as symbolic data. So every piece of the syntax of that language that he was interested in emitting, he devised a symbolic representation for it. In this case, closure maps. And when I say symbolic, I mean something inert, something that doesn't have methods or state associated with it, something that has a value that you could sort of manipulate as if it was any other value in your language. So that was his first move. He sort of symbolified GLSL. And the second move is he devised a way to use normal closure programming to construct that symbolified data. So you have a representation of GLSL that's all symbolic, and you have the entire closure standard library and ecosystem to build that data up. And at the last move, you snap it to life and it becomes a string, right? This was the approach. Talking about it more generically, given a target that you want to compile to, the first thing you do is you represent it symbolically. You come up with some kind of way, whether it's a bytecode or string concatenation, which is what Kovas had to deal with for GLSL. You come up with a way to represent it as inert values. And then you use some kind of expressive language to manipulate that symbolic representation into the shape that you want, and then you snap it to life at the end. This is what I call a symbolic compiler, right? This is a term that I made up, which is probably dumb. So if there are other better terms, please use them and inform me. But this approach is the thing that my compiler is built on, and that is what I'm sharing with you guys. So there's going to be a lot of really specific stuff because I think examples just speak much more loudly than me waving my hands. But really what it all goes back to is just these last two slides, is that this is an approach that I believe can be applied to pretty much any source and target within reason. So a lot of the research, my exposure to this stuff is primarily through Kovas. But I had a conversation with Kovas about where he got his inspiration from, and I've forgotten that nice man's name. And his name is Conal Elliott, right? So this is a researcher named Conal Elliott who, between 2000 and 2004, published some papers on embedded domain-specific languages in Haskell that would compile down to graphics primitives or to other like low-level forms. The first that Kovas mentioned was Vertigo, which was published in 2004. The other one was Compiling Embedded Languages, which is in 2003. I'll send links to to Software GR to post on the YouTube. So I haven't read these papers, but this is sort of what informed Kovas. This is the background. Also, the Terra project, which is a low-level Lua that interops with C, also has a series of publications that sort of relate to this. Although they're not quite doing symbolic compilation because they have their own sort of Lua syntax, but there's a relevance there. So that's some of the conceptual the background in the literature of this kind of stuff. It's not super new. I tend to think that doing it in Clojure is a little bit of a win over just about anything else. Another way to think about it is that you can use your high-level language to sort of steer your lower-level language, right? Because in my case, I know that I want to be emitting C# bytecode, right? I don't want to be writing C# bytecode. I know that that's the final thing, and I know what the shape of it is in my head, but I don't want to have to type all that out. So by doing it in this way, you can use the standard library of Clojure, for example, to just construct it for you. One way that Kovas has described it is you're representing the target in terms of the source language abstractions. So talking about bytecode in terms of closure vectors and closure maps and lazy sequences and all these like pure functions and all these wonderful things that we love. So some goals that I had while building Mage and Magic, and I think any sort of symbolic compiler like this should have. You really want to have your cake and eat it, right? I want to be as expressive as I am in any, on day-to-day programming, but I want to get all the benefits of low-level code. Benefits include some unexplored benefits on the C# VM. What's it called? You can call C functions from C# with almost zero overhead. You can do pointer arithmetic from C# bytecode, which, if you need to get your hands dirty, it's there. There are tail calls in the CLR. They're not super cheap, but they don't grow the stack. There's all kinds of stuff in the VM that to access, otherwise you'd have to hack the stock compiler, which is not a whole lot of fun. But being able to just emit the correct bytecode to do that, that's all of a sudden something a little bit more reasonable. Mage and Magic are libraries too. They're not compiler patches. They're just standard closure that just interops with C#. Composition. This is one of the, I think, unsung heroes of programming. I think a lot of entire ecosystems just fall flat on their face because code in their languages doesn't really compose. And a lot of the pain that I experience, and I see others experience in the JavaScript ecosystem, just getting stuff to just work, right? Getting your gulp to play nice with your browserify, to wrap your vinyl, like all these like, there's one thread in GitHub where someone was complaining about like some bug in some build tool. And I did a search on the page for ify, if-I suffix, and it was mentioned 122 times on that page, which is just not healthy. But composition is super, super important. I want to be able to take, bytecode level optimizations that were written for one compiler and apply them to mine, right? If they're just all talking about the same bytecode, there's no reason that shouldn't work. You should be able to mix and match and swap out parts of your compiler without breaking things. And a big sort of related thing to composition is locality. A big problem with the compilers that I've worked on is if I want to make one sort of conceptual change, I need to know the 40 places to make it in. And locality is the ability to sort of change one thing in one place and have that be the end of it. Pure functions give you that. Immutable data gives you that. There's all kinds of ways to achieve that. Full access to the target platform. This is unlocking things that maybe your compiler has not yet unlocked for you. You do not really want to make a new programming language with all the sort of difficulties of name binding and all of that. But you also don't want to make something that's just so full of like restrictive assumptions that you can't really express the sorts of bytecode that you'd want to on the target platform. So this is a lot of like these goals are sort of like I feel have focused me a little bit. And yeah, at the end, this is again something that Kovas said. He said that his goal was to make shader development more like normal closure programming, which is such an uncontroversial thing when you say it out loud. But that's also how I feel about compiler development. And what excites me about this stuff is that working on the closure compiler feels like working on any closure library. The difference being that you're actually building a compiler for this language. So the reason I use Clojure, it's because of all of these things. It's the only language that I've ever used that I've missed when I don't have it, like legitimately paying for. And these are all things, especially, I feel like the sort of live-coded dynamic nature of Clojure is really good for experimental stuff when you don't really know what you're doing. So working on video games, that's always the case. You never know what you're doing, right? You ship without knowing what you're doing, and you hope that people like it. But I also find that compiler work is a lot like this, right? There's 3 different ways to optimize this function. At the end of the day, sometimes it just depends on how the VM was written, right? It's like there won't be documentation on you use this opcode over that opcode. So you want to be able to try different things out without waiting a minute between each iteration and without breaking things all over the place. So in that way, I guess compiler development feels like video game development to me. But it's you don't have to deal with the App Store. So that's the sort of generic, general, like what I think symbolic compilers are, what I think they could be. I'll talk about next steps after I do my demos. I want to talk now about the more specific two libraries that I've built to sort of manifest these ideas and show you guys some code. So MAGIC is the Morgan and Grand emitter. And MAGIC is the Morgan and Grand intermediate language compiler. And these two libraries sort of, MAGIC is built on top of MAGE, and MAGE is sort of free of dependencies. And the two of them are what I'm using to build this compiler. So Morgan and Grand is the name of the cross streets where the Kitchen Table Coder Studio is in Brooklyn, which is me being completely adorable. And MAGIC is, you know, it's compiler stuff, right? It's like, it's real. This is how I see myself whenever I do this stuff. So MAGE is the symbolic representation of C# bytecode. Like I said, the first move is to represent your target symbolically. And MAGE is a separate library that just does that. You don't need really anything else. It just uses, closure interop to hook into the existing C# emission facilities, which are phenomenal, by the way. The C# reflection and bytecode emission machinery does not have to be as good as it is. It's just world class. And then MAGIC builds on top of MAGE, and MAGIC is a closure compiler, right? MAGIC isn't a generic, I mean, its goal is to just compile closure code as flexibly and as optimally as possible. And it's built on MAGE. Earlier versions, the version that I did the most work, used AST nodes from the existing closure compiler, which are like the C#, the Invoke Expert that I was showing you guys. But the version I'm going to show you now is much more raw, it's much more recent, and it's consuming nodes from Tools Analyzer. And for people who aren't familiar with the closure ecosystem, Tools Analyzer is a generic pure closure implementation of an analyzer for closure. So Tools Analyzer is able to take parsed closure code and produce a syntax tree in closure data. And it's very, very nice. It's functional. It's a little bit slower, but you know, it's a welcome trade-off sometimes. Huh. All right, now we get to write code. Ooh. So the first series of demos are the first set of demos that I have for you guys, just so we're all on the same page, is a crash course in MSIL bytecode. Who here has ever actually dealt with C# bytecode directly? I get to use my whiteboard. Nice. So this is tryroslyn.azurewebsites.net. Is this, I forget who put it up. It's been up for a while. It's just kind of always open in some tab in one of my browsers. It is an online C# compiler and disassembler. So I'll be able to write C# code in the top and see its IL disassembly in the bottom. I'm going to make it a little bigger. Is that size OK? OK. Oh, it goes side by side. Nice. So for example, if I have a function called foo, and it takes an integer and it returns an integer, with a bunch of stuff. This is a disassembly of the whole class. But if we scroll down, we can find, where is it? Method public instance returns an int32. Its name is foo. It takes an int32 as a parameter. And here's our bytecode. We load argument 1, and we return. So this is what that method compiles to. I'm going to write something a little bit more interesting and go to the whiteboard. So I add a second parameter, b, and I return the sum of a and b. Now we have foo, clearly takes 2 integers. And now our bytecode says load argument 1, load argument 2, add, return. Can anyone guess what the semantics of this bytecode might be? Stack language. Very good. So it is a weird stack language. So there is a stack that you have to sort of always envision in your head. And I'm very happy that there's a whiteboard here that's going to help with that. But the instructions run sort of from top to bottom. And there are go-tos and branches that we'll see in a second. And they affect this sort of invisible stack. So here what we've done is we've loaded argument 1 onto the stack. So at line 0, so after line 0, the stack looks like this. arg1. After line 2, the stack looks like this. arg1, arg2. And then after line 1, after line 2, if you would read the documentation on the add opcode, you'd see that its stack effect is to pop 2 items off the stack, sum them, and push the result back on the stack. arg1 plus arg2. And after 3, we return. So this is like a nice small group. If there are any questions, or if there's anything you guys want me to go over, please don't hesitate to jump in. I do teach for a living. So, so that's the basic idea, right? And it's exciting for me because I think stack languages are lovely, and I think you get a lot of composition for free just by being able to plug 2 sort of stack bits of stack code together. The subset of a valid concatenative program, or any subset of a valid concatenative or a stack program is also a valid concatenative or stack program if you build it right, which is wild. Like this is not true of almost any other language semantics. So we can have a little bit of fun with this. Maybe if A is greater than B, we do that. Otherwise, we return A. That looks like we load arg1, we load arg2. Anyone guess what blee means? Yes. So you jump if the argument on the top of the stack is less than or equal to the argument on the bottom of the stack. Again, you have to envision this thing in your head. And it does consume the elements on the stack. And you jump to line 8, which we see just loads argument 1 and returns. So this is the else branch. Otherwise, it falls through. It loads both arguments back again, adds, and then returns. So it's a stack language with go-tos, which is weird, right? It's not, people who've done like fourth or factor stuff, you don't have like line numbered go-tos. And we'll see once we get into Mage, how do you represent this symbolically? Because you have to. So that's branching forward. Let's say we want to return the sum of all numbers between A and B, right? So let's say something like, while A is greater than B, maybe I have like a, int f is 0, f plus equals A, A minus minus. Right? And we're assuming, doc string A always bigger, right? Because we're all good engineers here. So what does that look like? OK. So now we got a new little dot form. So the second way in which MSIL as a stack language is kind of funny is that it also has local variables. And it refers to them by index, right? So it basically maintains this array of locals. And here, it figured out that this method only has one local variable, and it's an int 32. So the first thing we do is LDC I40 st log 0. Any guesses what that might be? Exactly. It's this line. Yeah, perfect. So load constant 4-byte integer. It's like the matrix. You stop seeing these things like after a while. And there's some of the bytecodes have shorthand notation. So if f was some other number, it's load constant I4s, and it takes an operand, which is 34. So the bytecodes, the opcodes can have operands as well. But when it's 0 or 1, there's a shorthand that makes it shaves, I think, 4 bytes of your method size. And I think if it's a larger number, right. So S is for short, basically. It's a hint to the VM that it can be stored in a smaller size. Right. And then we store that into local 0. So again, the stack effect here, if we're gonna sketch this one out, so now we have locals, local 0, and we have the stack running through time. So at instruction 0, we've loaded the constant 0 on the stack. After instruction 1, the stack is empty because store local actually clears the stack. But now the value of local 1 is 0. The value of local 0 is 0. And then we do an unconditional branch all the way down to D. And this starts to look familiar. We load both arguments. We branch if the one on top is greater than, back to 4. And then this becomes basically the body of the loop. And some nicer disassemblers will actually indent this for you, because they'll figure out that you're doing a loop. Right? And then here you can see we load local 0. We load argument 1. And we add them. And we store that into local 0. So this is f equals f plus a. We load constant 1. We load argument 1 again. We load constant 1 again. We subtract them. This is a minus 1. And we store that into the argument a. So arguments are a little different from locals in this case. And then we do the comparison. So we have locals. We have labels. We have a stack to contend with. And that is the nature of MSIL. Calling a function looks like this. This is hello gr. Oops. Load string hello gr, and then you call and you pass it in basically the function pointer, and it calls that function. So this is what MSIL bytecode looks like. And I wanted to do this before getting into the MAGE stuff because it makes much more sense when you sort of have at least some exposure to the target that we're dealing with. How's that so far? OK. Now, on to MAGE. This is where we take a deep breath, because I have all kinds of crazy tech just sort of strung together. So this is what a full MAGE thing looks like. It wraps the entire emission API. So it's not just the bytecode that you find inside a method. It's able to describe types. modules and assemblies. It has to be able to do that. So here we're creating an assembly, which is basically a module inside an assembly is basically like a binary that you're emitting in C#. We're going to create a type that's called example type. We're going to create a method that is called add integers. It returns an int32, and it takes two int32s. And then this is its body. Load arg1, load arg2, add, return. That's what we saw before. And if I run this, how's that code size? A little bigger? Make it a little bigger, never hurts. And you'll see the results in my REPL down here. The result of evaluating that form, this is closure map, not super important. But now if I evaluate this, example type is all of a sudden a type that exists. And if I run this line, I get 1 and 2 sum to 3. So for those less familiar with closure syntax, I'm creating a new example type instance, and I'm calling the add integers method with the arguments 1 and 2. And the result that I get is 3. Not bad. Right? Just so you see, it's not like a gigantic animated GIF. Maybe it is, it's unknowable. But this is pretty cool, right? And so what is this stuff, right? What happens if I just evaluate IL LD arg1? It's just a map. What happens if I evaluate this whole vector? That's just a map. That's just a vector of maps. So this is the bytecode body of the method represented symbolically. This is just closure data, right? I can type this in. Oh, I have to sort of quote it correctly. But you could reproduce this map by any means necessary, and that counts as symbolic bytecode. All of these functions do is just return these simple little maps for you. Kovas calls them constructor functions, because they just they're a succinct syntax to just produce the sort of maps that you'll be using. And this is true for everything. Even if I evaluate just method, it's this growing, larger map. And I'll turn on pprint. So the method represented symbolically is mage core begin method, and the argument is, the name is add integers, attributes are public because this is the default, return type is int32, parameter types, system int32, int32, and then the body. Again, the IL method function just produces this map. None of these are doing anything interesting. They're just sort of moving your strings and your values into the correct place in the map and just giving you that map back. This map is harmless, right? It's persistent, immutable data. And you can deal with it the way you deal with any data in Clojure. And this is true all the way up to assembly. And the assembly and the module are similarly described. One really nice thing about MSIL being a stack language is Mage allows you to sort of nest things in vectors as much as you want, because it's convenient to return a vector of things. And the first thing it does is flatten and just runs through all your stuff. So you'll see a lot of nested code, just because it's sometimes more natural to write that way. But it's semantically meaningless because it's just a stack language. So we just flatten, eliminate all the nils, and then we just go through and emit all the the requisite bytecode. So that's the first step, right? Is being able to represent all this stuff symbolically and manipulating it. Let's see if my other bit of fun is playing nice. OK. Now, it would be really cool if we could, yes. It'd be really cool if we could live disassemble this symbolic bytecode that we're compiling, which is less to do with theatrics and more to do with really one of the very first slides that I had, which is the experience of writing code. And I think live coding is one of the absolute most categorical differences in my workflow that I've ever had, well, as a programmer. So everything that I do, I try and bring a sort of live coded workflow to it. So being able to see what I'm doing, like as I do it, is very important. So I can switch. This is a little disassembler that I built that is just reading the binary that we're producing. And you can see here, this is the bytecode that we just spat out. That's visible to everyone. So if I were to change this to sub, and now we're going to subtract, we'll see that is sub, right? Which is pretty cool. And we can render it back into C#, which is kind of amazing because this is like no one ever wrote this code, right? And someone was looking for like Unity game developers, and they didn't want to use Arcadia. They wanted a C# code base, and Tim's was like, "Fuck it, we'll just disassemble it into C# and just deliver that to them." Like, what do they know? They'd know. It's not like anything beyond something this trivial just becomes completely unthinkable C#. But I have a couple more demos that I want to show you guys in this. So what does this guy do? Right. So admit that. So this is a similar one, except we can see from the C#, it now is taking two objects, casting them to a longs, and then recasting them to objects on the way back. Why would you do such an unthinkable thing, you think? Well, you might be trying to reproduce closure, like the way Clojure does numbers sometimes on the CLR, with a lot of boxing of value types. So this is what like untype hinted Clojure would do in the worst case. It just casts your numbers to objects. The interface for functions in Clojure is called an IFN. An AFN is the abstract function. It's an abstract class that you inherit from. And every function in Clojure shows up as a type, actually, as its own type in the binary, and they all inherit from AFN. The Clojure specifics aren't super crucial, but the point is that I'm able to sort of emit and use that code immediately, right? If I decide to subtract that, now I have -1 again. If I decide, maybe I want to subtract, maybe I want to add the first argument to itself and ignore the second argument, that'll be 10, and that'll be 30, and this will be ignored. So the contents of this code shouldn't be blowing your mind. The fact that I'm able to live code and sculpt bytecode and rerun it and then spit it back in, that sort of tight loop is what has been my goal for the last year building this tech. We can get a little crazier. So because the stuff that comes out of this is consumable by Clojure, we can wrap the whole thing in a def. And we get some reflection warnings, because believe me, we're doing some reflection. And now we have something that looks like totally innocent Clojure function. Hey, no, I wasn't generated by insane symbolic bytecode. Who said that? And to get beyond adding a little bit, we can, did I get this? Oh, no, I didn't finish this last demo. I was working on, this is my like safe file. I'm about to move into the sort of file of nightmares. But I was working on a for loop demo for you guys. But that's what using this sort of symbolic stuff looks like. Those are the demos that I could sort of like most stably put together. I'm going to spend a little bit of time going through MAGIC itself in its current state. which uses this kind of stuff to like the nth degree. But that's going to be more of a tour of just the existing code and like evaluating it. So Magic, we should still be in the namespace. So this is what Magic looks like. So Magic at its heart, right, good. So let's say you have a function, right? Function A that, you know what? That does that. So if I were to, you know, compile this in Clojure normally and run it, I get hello gr, right? So it's a function that takes an argument A that calls stir, which constructs a string out of all of its arguments and returns the result. What the Magic pipeline looks like is this. The first thing we have is the parsed form. So I put a quote at the beginning to prevent it from evaluating. The first thing we do is we pass it through the tools analyzer. And we get a big map. Just took a second to compute, if you notice that. So this is what the syntax tree looks like as far as tools analyzer is concerned. It's for this tiny function. So some of these things become unprintable, but because of the way structure sharing works in Clojure data structures, all the repetition doesn't actually happen in memory. They're just like all the sort of repeated structures are just pointers to each other. So printing it is actually difficult, but actually using it is not, which is kind of a weird inversion. But I mean, it's great. It's like functional. It's persistent data that you can consume and manipulate and operate on the way you would any other bit of Clojure data. The next thing that we do, so far this is just tools analyzer, and you'll see that they put a lot of richness into your that comes along with your code. I should just do a quick little. So the body of your function. Sorry, the body of your function knows that it's a body. Where did I go? It keeps track of all the locals that were mentioned in it. The locals know, their original form, how they were created, and so on and so forth. So it's just much richer than reading the source will ever be. So then the next step is, and this is where my architecture kicks in, and this is where it only becomes possible using Mage. You pass it to what's called what I call a symbolizer. You can't symbolize pprint, but you can pprint to symbolize. Boom. And the symbolizer is what produces the bytecode. So the Magic pipeline is source code, persistent data, AST, persistent data, symbolic bytecode, persistent data. So these are all it's a clean movement from what you wrote to what the final bytecode will be. And what a symbolizer is, so oops. So a symbolizer is just a function that takes some AST and produces bytecode from it. That's the idea, right? Tools analyzer can take source and produce an AST. Our symbolizers will take AST and produce bytecode, and that's just the next step. But it's built in a way that is somewhat exciting. Let's look at Invoke. So it looks up the op key in the AST. Tools analyzer has this convention where every bit of AST that it gives you back has an op key in the map that describes what that thing is, basically. Is it a vector? Is it an invocation? Is it a var? And then each one of these is passed to the correct function, along with a map of symbolizers. So invoke, there's a special case here for if it's a host interop form. But what it bottoms out is you symbolize the first thing, the function. You cast that to an IFN. You map the symbolized function over the args. And you symbolize the args and you convert them all to objects. And then you call invoke. So if I compile instead of just symbolizing, if I actually compile this, we should get, so that compiled, and I'll start watching that file. So this is the compilation of this function that just prepends hello to whatever you pass in. It looks up the closure core stir var, casts it to an hyphen. Oops. And then invokes hello with the second argument. And if we look at the bytecode, we load the string closure core, we load the string stir. We call the var, RT-var function. So basically, we're going to look up this var. That's what this means. So now the actual var is sitting on the stack. We call get raw root, which is we get the current function that var is referencing. These are closure-specific semantics. But so at this point, we have the actual current str function sitting on the stack. We cast it to an hyphen. We load the hello string, we load the first argument, and we call invoke, and we return. Now, there's a few things that I want to sort of point out in this, and then I'll wrap up. If we go back to the invoke symbolizer, where did all this come from? So we didn't hit any of the special cases above. When we look in here, it's calling var, it's calling RT-var, it's calling get raw root. That doesn't happen anywhere in this code, right? But when we symbolize the str, the first sort of the first form, we hit the var symbolizer because it's a different kind of AST node, and that returns load var of the var, and then get var of the var. Load var. To load a var, you load a constant, which is the name. This is the first load string. You load a constant, which is the namespace. This is the first load string. You load a constant, which is the symbol name, which is the second load string. And then you call RT var. So I just showed you 3 functions, right? Each one of those functions produces a tiny bit of symbolic bytecode. And that bytecode, by returning values and sort of being nested inside of vectors, builds up the final bytecode. Each one of these functions is completely harmless. It doesn't set any state. It doesn't, trigger any kind of mutation of anything. They're all, and they were tested in isolation, built separately, interacted within the REPL. I could just call load var closure core plus. And that's what that looks like. I can look at what the bytecode would be if that function was ever called on that. I can call load var on load var. Why not? Similarly, I could also call the var symbolizer on a mocked up AST node that I may have made, right? So at every level, this is completely inspectable, completely intervenable, and just alive, and you're able to sort of like loop and iterate like that. So that's where all these like extra other bits come from. So this is, all this is I'm doing real functional programming, like dynamic live coded functional programming to do compiler development, right? The last sort of trick that I'm kind of proud of is the let symbolizer. Let's actually look at a let compilation first. Because this is one of those things that maybe is a terrible idea. It's probably not a terrible idea. We'll see. So function takes in A, right? Let's say B is A incremented. And we're going to print out B. And there's another let binding in there. And then C is, you know, B times 5. And we're going to return A plus B plus C. Oops. So there's a couple things going on here, right? We've got an argument. We've got two let bindings. They're referring to each other. Most importantly, it works. If you look at the C#, you know, object is the arg incremented, and then we call print line on that. And then argument 2 is object times 5, well, 5 invoked on object and 5. And then we return plus of arg, obj, and arg2. So there's some shenanigans going on here, right? There's like something less than trivial. And to me, getting this, the let symbolizer to work was a sort of moment of, oh, I think this is going to work. The whole thing is 30 lines of code. There's no external state to any of the let, to any of the symbolization process of let. I think in the closure compiler, it's been a while. I forget how it's done exactly, but I think there's a place where the locals are kept. And basically the problem is, as you descend into the body of a let statement, you're encountering names, and you need to know to swap them out for local variables, right, that are being like stored and updated. So there's a place where locals are kept and referenced. But what we do instead in MAGIC is the first thing we do is we build a binding map where we reduce over the bindings in the let AST node, which if I were to do an analysis of it, one of the things that Tools Analyzer gives you is all the bindings that are in that let expression. And we build up a map of the local node, the AST node that will represent a local variable somewhere down the line. We map that to an IL local. So this is how Mage represents local variables. It creates these unique or gensim like identifiers that can then show up anywhere in the bytecode and will get stitched up back together. So now we have a mapping of every local variable to some kind of unique persistent value that just represents it and knows that it's correct type. So now we have this binding map, right? We do some stuff to deal with recur, because you can let bindings are basically loop targets in closure. That's like less important. But then we do this. So every symbolizer takes as input the AST node that it's producing symbolic bytecode for, and the map of symbolizers that it should use. We construct You only do this for like if statements or let statements. You don't do it for most forms. But in this case, we construct a new symbolizer that is the old symbolizers, whatever was passed into us, and we replace the symbolization of local variables with this function. This function looks up the name of the variable that it encountered. It looks it up in this binding map that it is closing over. And if it finds it there, it emits a load, a bytecode load for that local. Otherwise, it symbolizes that thing with the symbolizers that the let expression was passed in. So it's a little bit of a computational ballet, but it keeps the entire thing completely compact, right? And the state of your local bindings is then maintained in this sort of chain of closures through the invocation of the symbolizers. And this is something that if any one of these functions was updating any kind of state anywhere, would be unthinkable, right? This is only possible because I can just return because I can do this in one line. Just load the local. I don't know or care where this is going to end up, right? Maybe this is going to get emitted to disk. Maybe it's just getting printed out. All I know is that semantically, if I'm somewhere deep in the let body and I match a binding that was like declared higher up, I should emit a load local for that, and everyone goes home. That is the sort of strength of approaching compilers like this. You have this compactness, and now if I ever need to tweak the way let bindings work, I have 30 lines to worry about, and absolutely nothing else, right? You get other things where, this is a fun function, convert. So converting between types is something you have to do in any language, especially in a dynamic language. We lose a lot of performance from really sort of sloppy type conversions. So I spent an evening, and I did a bunch of research in Microsoft documentation, and I built the matrix of how to convert anything to anything else on the CLR optimally, and it's in this function. And it's a lot, because there's a lot of cases, but this is it. There's just no other way to convert between two things. And now everywhere in the code, I see bytecode that surprises me by how clever it is. It won't double convert to a float, for example, and stuff like that. That's just because I use convert from to everywhere, right? It's just a pure function that just takes two things and returns a little bit of bytecode that converts from the one thing to the other thing, and that's all it ever does. This is the kind of stuff that makes writing a compiler less crazy, I guess. There's still a lot of work to be done. But the ability to sort of do this stuff incrementally and see what you're doing and query it has been really, really powerful. So I want to wrap up because did we lose everything? Oh, ha! I was just on that slide. So that's sort of where I'm at, conceptually and in terms of building the biggest manifestation of this idea, which is magic. But I do think that this is a generic idea that could be applied to really any target that is well-reasoned and ideally has some kind of emission framework. Again, Kovos built Gamma, which by concatenating strings of GLSL, so you could do that too. But I'm excited to try this out with LLVM Bytecode, which is lower level than MSIL and has interesting semantics that are kind of a little bit daunting, but has an emission framework and is very, very well reasoned. So the idea that you can steer machine level code from closure is all of a sudden not so crazy. Mage is actually almost done. It needs to support nested types, and there's one or two other things. But as just a wrapping of the entire C# emission API, it's almost, there's not a whole lot more to do. Both of these libraries are on my GitHub. MAGIC was going to require quite a bit more work to just sort of completely compile all of closure. I can show you, hold on. The tests are great. These are my favorite Yeah, these are my favorite tests that I've ever written, I think, for any language. So test same. Yeah, test same is a macro that evals a form in Magic and then evals it in Clojure and just tests for equality because you just have equality semantics. So it just like double compile and compare everything. It's just kind of great. So yeah, there's quite a bit of work to be done there. Part of that is building out the analyzer, which is something I didn't talk about today, but the C# specific portions of the tools analyzer chain don't exist. There is a tools analyzer JVM. There is a tools analyzer JS. I will probably have to write tools analyzer CLR, which is fine. And that just gives the sort of rich sort of type-specific information that we need to emit optimal bytecode. And beyond that, we have a metacircular symbolically compiled generic function Lisp on the CLR, and everyone's happy. So that's all I've got. If you guys have any questions, I'd love to take them. But thanks for listening.